Okay, next, let's look at the properties of t-distribution. Okay, the first one is we summarize what we get on the previous discussion about the model assumption of t-distribution. Given x1 up to xn is a simple random sample from a normal population. Okay, in this statement, we make two model assumptions. One is simple random sample assumption, and the other one is normality assumption. Okay, after making these two assumptions, we say sample mean subtract by population mean over sample standard deviation divided by square root n, follow a new distribution called student t-distribution. Okay, and later on, we're going to also tell you simple random sample assumption is more important than the normality assumption. The reason will be explained later, okay? Now, property 2. Student t-distribution are symmetric density curves. T-curves are bell-shaped, just like what? Just like the normal curves. Okay, just like the normal curves. Property 3. Each t-distribution is associated with a specific degree of freedom. The degree of freedom denoted by df or use a Greek letter nu. Nu, okay? This is nu. This is a very common one, very standard notation. Almost all the book, when they refer to degree of freedom, they use nu, okay? And what's degree of freedom? Let's look at comments on degree of freedom. Given x1, x2, x3 is a sequence of independent and identically distributed random variable, or you say they are simple random sample. We focus on what? Independent. When we say x1, x2, x3, they are independent. What does that mean? That means x1 can change freely in its own direction. x1 can change freely on its own direction. Without being affected by x2 or x3. And similar argument apply to x2 and x3. That is to say, x2 change freely in its own direction without being affected by x1 or x3. x3 change freely in its own direction without being affected by x2 or x1. So in this case, all three directions can change freely. So the degree of freedom for this collection is 3, because all three directions, they can change freely. However, let's look at the next one. This collection, x1 minus x bar, x2 minus x bar, and x3 minus x bar. The degree of freedom of this collection is no longer 3. It lost 1 degree of freedom. It has only 2 degrees of freedom. Why it lost 1 degree of freedom? Let's see. Claim x1 minus x bar plus x2 minus x bar plus x3 minus x bar. They must add up to 0. Okay, why is that? Okay, why is that? Let's see. x1 plus x2 plus x3. x1 plus x2 plus x3. Subtract x bar, subtract second x bar, subtract what? The third x bar. So subtract 3x bar. But what do you know about x bar? X bar is x1 plus x2 plus x3 divided by 3. So after cancellation of this 3, it's x1 plus x2 plus x3 minus x1 plus x2 plus x3. So this must be what? Equal to 0. That is to say, if this one change freely, say I ask a student assign any number they like for this one, and the student says 3, okay? So the first student says 3, and I ask a second student, give me any number about x2 minus x bar. The second student say what? 24. Then the third term, x3 minus x bar, cannot change freely, right? The third term has to be what? Has to be minus 27. So they can add up to 0. So only 2 of them can change freely. The last one, subject to this constraint, must add up to what? Must add up to 0. So you can only have 2 degrees of freedom. You don't have 3 degrees of freedom. And why is that? Well, minus 1 is what? 1 constraint. This is 1 constraint. Because this constraint, we lost what? 1 degree of freedom. Okay? Is that clear? This is the concept of degree of freedom. Now, let's move on to the next page. Okay, let's move on to the next page. X bar minus mu over S divided by square root of n. Okay, sample mean minus by population mean over sample standard deviation divided by square root of sample size. This is a t distribution. This random variable for our new distribution, t distribution, with degree of freedom equal to n minus 1. And let's see, why is that? Okay, the above procedure is called one sample t what? T procedure, okay? And in one sample t procedure, the degree of freedom is what? Degree of freedom is n minus 1, okay? So why this degree of freedom is n minus 1? Observe that t depends on s. T depends on s. And s depends on, this is s, the sample standard deviation. S depends on x1 minus x bar, x2 minus x bar, up to xn minus x bar. So let's try one more time. T depends on s, t depends on s, and s depends on x1 minus x bar, x2 minus x bar, to xn minus x bar. What's the degree of freedom? Huh? Because x1 minus x bar plus x2 minus x bar plus all the way up to xn minus x bar, add up to what? Add up to 0. So you lost 1 degree of freedom. The degree of freedom is n minus 1. Okay, so let's one more time. T depends on s, and s depends on this, and this has only what? N minus 1 degree of freedom. So this t has what? N minus 1 degree of freedom. Okay? So t equal to x bar minus mu over s divided by square root n has n minus 1 degree of freedom. Notation used, sometimes use t nu equal to n minus 1, or just t sub 1, n minus 1. Okay? I think this is a time for me to explain. Recall, if this is population standard deviation, x1 minus what? Mu squared plus all the way up to xn minus mu squared divided by n. Remember at the beginning of the term, I say if the least x1 up to xn represents a population, when you divide it by what? When you're taking average, you divide it by n. But if this is sample standard deviation, you should divide it by n minus 1. And why is that? As I just mentioned, if this is a sample, x1 minus x bar, x2 minus x bar, up to xn minus x bar. Only n minus 1 of them can change freely. So when you're taking average, you should divide it by n minus 1. You should not divide it by what? Divide it by n. And here, mu is an unknown fixed constant, has nothing to do with x1 up to xn. So x1 up to xn, they are IIP, right? So you have what? You have n degree of freedom. So all n direction can change variability. So when you take average, you divide it by n. But for sample standard deviation, only n minus 1 of them can change variability. So when you take average, you divide it by n minus 1, okay? Let's take a short break here.